Relax.
Welcome everyone to Machine Learning Research Week here at IIT Guwahati. For today's talk, I would like to introduce you to Mr. Abhishek Kumar. He's currently the Director of Data Science at Publicis Sapient, where he's focusing on methods to utilize deep learning for retail, e-commerce, and more. Apart from this, he's also recognized by Google as Google Developer Expert in Machine Learning. He's authored many successful courses for data science on Pluralsight and delivered numerous great talks globally in globally renowned conferences. Now, without further ado, I'd like to pass it to Abhishek. Please take it over.
See, logistic check. Is my screen visible and am I audible? Can you see me?
Yes.
Okay,
Yes.
cool. All right, thanks everyone. Thanks for joining in, and that too probably on the evening. So today I'm going to talk about a pretty interesting topic, which is recommendation engine. And the good part about recommendation engine is that this is something that all of us deal with almost on a daily basis. And we are trying to see it, how can you use graph and graph neural networks to build such kind of a new age recommendation engines. So that's a topic for today. Um, and so already we talked about the introduction done, but if you want to just probably reach out to me on LinkedIn or Twitter, here is my Twitter handle, though I'm not a very avid Twitter fan, but definitely reach out on LinkedIn. All right. So with this, here are the three goals for today's session that I had set it out. And hopefully that we'll be able to meet all these three goals. The first one is giving all of you a high level overview of what exactly a recommendation engine is, and what are the key building blocks that are needed, and the challenges associated with building a robust recommendation engine. So that is going to be the first part. And the second part is we will look into what are the some of the motivation behind why you should opt for a graph and a graph representation. And then we'll get into some intuition around using how do GNNs or graph neural networks work, especially in the recommendation system context. And I'm not going to probably go enough level of detail for all of the possible architecture, but my job here would be is to give you enough intuition and different variations that you can utilize and go deeper if needed for your own application, your own use case. And towards the end, based on how much time we'll get, I'll try to give a teaser around while all of these small scale POCs are fine, or maybe building some of these small scale solutions. But what a real world recommendation system looks like, what are the different ingredients that are needed to make it successful. So with that, let's jump into the first section, which is a recommendation engine itself. Like I mentioned, recommendation engines or systems are everywhere. And I don't have to convince all of you is that why you should be reading about recommendation engine, because all of you have been dealing with it, right? Day in, day out. So if you buy products or books, maybe on Amazon, that's your product and book recommendation. Similarly, if you are on Facebook or maybe on any other social channels, they recommend friends. LinkedIn happens to recommend jobs or maybe a contact on to which you want to connect to. iTunes recommends songs, Netflix recommends movies or series, and then you have Coursera or Safari, they recommend books and courses, and Spotify recommends music, right? So I guess if you probably pick up any kind of an application, you'll find there are certain elements of recommendation. And why it is needed? Because most of these organization, the companies that you have seen here, they may have multiple products, right? Maybe hundreds and thousands, and for some it could be even million. And how they can surface more important um, products and services in front of their customers, so that obviously they go for it, they buy those things or they subscribe to those services, and eventually become a loyal customer for them, or obviously leading to more revenue. So hence recommendation engines are absolutely critical for almost all of the organization. Now, what exactly is a recommendation, right? So on a high level, if you have to define this, It is how do you serve relevant items to users in an automated fashion to optimize short-term and long-term objectives, right? And we have highlighted these words and we'll try to talk about what exactly it means. So when I say relevant, it means is we are answering what. So you want to make sure the recommendations that we are generating, those are novel enough. We are also trying to bring in some kind of a serendipity, which is some newness, and it should provide a diversity. So for example, if you are looking into, let's say, Amazon, you don't want to see only one kind of a product. You also want to see other kind of a products, and that is also needed, especially for clients or organizations with many number of products. What I call as a long tail problem. So that means is you may have many SKUs, potentially millions of them, which you also want to surface for those users. Then we want to ensure that the system is automated, because we don't want to sit and manually craft recommendation for all of the users. So we want a system which requires no or very little manual intervention, and that can scale up as the client and the organization will scale. They have more users or more products or SKUs, how the system can scale. And there are certain business objectives, which is their short-term business objective or long-term. Short-term could be is they want to look for more clicks, a higher revenue, more explicit positive ratings, or it could be long-term business objectives where they want to ensure that by providing a better recommendation, it is leading to a better customer experience, and hence it would be more engaged customer, and maybe also later on more subscriptions. So how does it work? So if you look into most of the recommendation engine internals on a very high level, they might look like the same, which is you take the information maybe about items, right? What are the different items which are out there? You put it into probably some kind of a machine learning model. You also want to introduce who are these users, what is their profile, what's their intent, and maybe also some context. It could be location context, it could be time context, it could be maybe just day of a year context. For example, if it's a Black Friday and you want to push more of an electronic items, or if it's a seasonal, which is, let's say, it's a winter season and you want to push more winter season related items. And then last but definitely not the least, you also want to account for different interactions. So for example, how the different users have reacted to different products, whether they have clicked it, whether they have like given some thumbs up, or whether they have added to the cart, or they have viewed their details. So we would like to utilize all of these interactions and feed it into this machine learning model. But ultimately, this machine learning model is going to spit out scores. What it means is that for every single item in the list and for a single user, you want to score what is the likelihood that this customer or this user is going to buy or probably click or share that particular item. And once you have this set of scores, what you want to do is rank these items based on different business objectives. So for example, you may want to just sort it based on the probability of click, or you may want to still push, let's say, some of the latest I don't know, fashion, right, or some of the latest product, or maybe high margin products upfront. So you can apply a lot of business objective there. So these are some of the internals. Now let's talk about what are the key challenges. So the biggest challenge in a typical recommendation system implementation is how do you even represent these users and items? So what are the best way to represent them? When I say represent them means maybe let's say put them into some numbers, right? Because you have an ML algorithm, and ML algorithm obviously acts on these numbers. So how do you even represent that? What exactly a user representation means? What would be an item representation? The other key challenge is that you want to build a hybrid recommendation system where you can take into account both the interactions as well as whatever the additional information that you may have about the user or about their item, what we call as metadata information. And then there are challenges around how do you essentially mimic the dynamic user behaviors, because user behaviors are also changing, or you may have additional information that you might get down the line. So how do you even use that? And then how do you use different feedback beyond the explicit feedback? So when we say explicit means You provided certain item to the user and you asked the user whether you liked it or not. Uh, Obviously, Netflix used to do that earlier, but it's very challenging, right, to get explicit feedback. So you want to rely more and more on implicit feedback. So, for example, whether you have viewed certain TV show or not, or whether have you shared it certain products with others or not, right? So how do you use all of these implicit feedback signals in your recommendation engine? So with that, hopefully you have a basic understanding of what exactly a recommendation engine is and what are the different ingredients that goes inside a recommendation engine. Now what we're going to talk about, what is the motivation for moving to a graph and a graph representation. So let's take an example. So let's take a step back, right, and see how these systems have been built in last few years, right? Recommendation engine is not a new problem. It's being solved over the ages. A lot of techniques have came and people have tried so many things. There are so many research articles and there are entire conferences dedicated on recommendation system. So I'm going to pick one of the most popular one and that you might find in most of the even introductory books as well, which is collaborative filtering, right? And one of the first step that we typically do in a collaborative filtering, and especially one family of algorithms which you call as the matrix factorization, is that you try to create this interaction matrix. So let's say that you have different users, these 4 users we have, and we have 4 products, and then you can create this matrix and you can fill in this matrix. So for example, if this particular customer has maybe clicked on a backpack, so maybe we can give some weightage to this particular interaction. Then maybe if this particular customer has, let's say, purchased this particular item, then maybe we can give a more stronger interaction signal. And then maybe we don't have these gray dots essentially represents that we don't have signals on these user and item combination. So if you boil down to what exactly the recommendation engine problem is our ability to fill in these blanks. So suppose that if we are able to fill in this blank, that what is the likelihood for this customer, the second customer, to go for maybe an office furniture setup? Our job would be done. And hence there are a lot of approaches which are there that kind of tries to solve this problem by filling in this metrics. And one of the way that we do it using a very popular technique, matrix factorization, which also happens to won the Netflix $1 million challenge, very famous. So what we do there is we try to create a latent factors. In a way, you can think that as some kind of a representation for every customer or user. So let's say that we are representing every user with 3 numbers, right? So these numbers we obviously learn during the training process. And similarly, we have a representation for every item. So we call that as latent factors for items. And our job is, once we have these lower rank matrices, U and I, we try to compute probably this multiplication of these U and I to come up with some resultant higher order metrics, which is nothing but filled value for the entire thing. And obviously, we use some kind of a loss function over the period so that to train the model and eventually come up with this representation. So in a way, we are already doing some kind of a representation. The challenge in this representation is this is using what we call as a shallow encoding approach. So what exactly it is? So what we do is we try to create an embedding matrix, which is nothing but a very simple lookup, where you can think that we have 1 column per node. When I say node, it can include both user as well as items. And then suppose that we have an embedding size. So let's say that in this case, we have an embedding size of 3 because we are trying to represent every user and item in 3-dimensional space. So now suppose that we have this matrix, which is 1 column per node. But while this is great and this works, there are certain limitations for this approach. The first limitation is, first, if you see the complexity itself. So if you have more number of nodes, we are talking about maybe millions of users and maybe billions of products, and suddenly this embedding matrix that you have to learn, the size it be pretty huge. And that obviously is a very challenging ask, right? So, for example, how do you even train it? And it will require massive computation. So while obviously that is scalability is a bigger challenge, the other challenges are that suppose that if we have trained a model with certain set of users and items, if you have a new node, when I say new node means a new user, or maybe a new user has joined your platform, or a new item has been introduced into your ecosystem, we do not have any representation for that particular node. And that means is it cannot, suppose that there is a new user, it cannot make prediction for future, right? And that means you have to again retrain the model. And as I mentioned, that retraining is obviously a very highly computational intensive task. And more than that, here if you see the way we have created and learned these latent factors, we are only relying on these interaction, right, which is clicked or purchased. We are not using the node features, which is some kind of node attributes around user attribute or item attributes. While there are certain variations, by the way, of even for the matrix factorization and all that uses, but most of in general, these approaches, they do not incorporate these node features. So how do we solve for it? So we understood that there are certain limitations of existing approaches. And now we'll see how graphs can help and come to rescue. So let's look into the graph. So if you look into any graph, by default, you can say that a graph can represent all of these nodes that we are talking about. These could be users, these could be items. And the linkage between different nodes can represent the interaction. The interaction can represent whether it was bought, it was clicked, it was shared. You can have more than one links. The strength of the link can represent the how strong that relationship is. So that's the representation part. You can also have associated attributes for every node or every edge. So for example, you can have all of these vertices, the gray dots that you see, and you can associate certain metadata attributes. That could be user attribute, that could be item attribute. So all in all, it's relatively easier to model all of the different factors in a graph. And that's where obviously it is very popular, and the graph are becoming popular in the recommendation engine world. So what we do is what I call as graph representation learning. And this is the core behind most of the things that we're going to talk today. So what exactly graph representation learning is, suppose that you have a graph on the left-hand side. We would still want to create an embedding, which is nothing but a representation, some numeric representation in this embedding space. So suppose that we have this node and we want to come up with some encoded embedding that is, let's say, ZU, and let's say this node V is, and we want to come up with ZV. And the idea is that in these values, right, Z, Z, E, and ZV in the embedding space, if we compute the distance, that should be very similar to how they are in the graph space as well. So for example, if these two nodes are neighbors, that means is even in the embedding space, the distance between them should be relatively smaller than others. So this is what the notion behind graph representation learning is. And one of the other benefit, we talked about how graph can be useful to probably put different kind of data, right? You have user data, item features, you can probably put in interactions. But one of the biggest benefit is what called as an inductive capabilities. So suppose that you trained your, let's say, model using some set of nodes. So you have this training data. And suddenly a new node arrives in the graph. That could be a new user, that could be a new item. And now, in order to get a representation of this red dot, you don't have to retrain the model again. But what you can do is you can simply use the neighborhoods and their aggregation, some kind of an aggregation logic to compute the embedding for this red node without retraining. And that's a massive, massive benefit, especially if you're talking about large scale systems where more and more users are getting onboarded or more and more items are getting added. So hopefully now you're convinced that graphs are good well suited for a recommendation engine kind of a problem, let's see that how we can essentially train such kind of system and build such kind of a system. And one of the easiest way and very popular is what we can do is we can take this interaction metrics that you see on the left hand side. We can simply take that and convert into a graph form. In this case, we are creating what I call as a bipartite graph, which nothing but you have one set of nodes which represents users and one set of nodes which represents items. And as you can see, what we have done is we have taken this all these four users, put it here, and all these four items and put it here, and the relationship. So, for example, if this user has clicked on the backpack and we created this yellow kind of an interaction, right? So that is your edge. And maybe if this user has bought the second item and we created this green one, which is a purchased interaction. So as you can see, it's pretty easy to convert an interaction matrix. So we move from a matrix setup to a graph setup. Now, once suppose that we have a representation for all of the nodes in the graph, the problem statement essentially translates into, if we have to do a recommendation, a new set of products that we want to recommend to, let's say, this user, we have to just identify whether what you call as a link prediction. So what is the weightage of this particular link? So in the training data or probably during training process, obviously these were, we don't have this relationship, but we would like to compute a score for this particular line, what we have marked as question marks. And that is what the entire recommendation engine problem statement here. So now let's see how you can learn the representation of all of the different nodes and how you can make this prediction of the scores for making the natural recommendation. And that's where we are going to use graph neural networks. And I'm going to give you a very high level intuition without going into too much of nitty-gritties about how graph neural networks work and all, right? So just to give an intuition that on a high level, how it works. And one of the biggest thing that happens in a typical GNN setup, you might hear this term as if you have encountered this area before, is called as message passing. It's really very intuitive as well, and we'll see how. But this is a very core technique that is being used in a graph neural network setup for training such kind of models. So what we do is we start with, let's say, some kind of initial representation. So let's say that we have this user and we have to give some initial user embedding representation where we can simply use, let's say, user attributes. And it could be, let's say, gender, their demographics, there may be preference, and we can use that to represent initial value for the user embedding. So let's say that if it is a gender and if say it's a male or female, let's say 0 and 1. So this representation becomes 0 and 1. Or suppose that which city this particular user belongs to, and maybe we have a representation for that also. So likewise, we can have a representation for all of the users. And then you can also have some initial representation for all of the items. So for example, let's say you can use item metadata attributes. For example, which gender this item typically is being used by, right? So if it is male product, female product, or you can also use, let's say, text information. So let's say that you have a title of a product and you may want to use a word-to-vec representation or a globe representation to probably put forward what is this item representation is. You can combine multiple representation as well. So for example, you can take an image of a product and come up with some representation, maybe using, let's say, VGG or Inception kind of a model, and concatenate with a text information coming from a word-to-vec. And we'll see that how some of the organizations like Pinterest use very similar technique for making recommendation engines. So this is your initial setup. And once you have this setup, what we do is we do a message passing. So what does it mean? What does it mean that you take all of these representation and then pass them through some kind of a neural networks. So let's say that we are focusing on this particular user, the first user on the left. And then we look into, okay, this user is connected to, let's say, these two items. So we take these two messages on the items and pass them through the neural networks to get some kind of a representation. So this is an outcome of that neural network. And once we have this, this for every user, we identify who are the neighbors. In this case, these are the two items that are connected. So what we do is call as a neighborhood aggregation. So we take, okay, this user has probably two more messages coming here, and then it had its own representation also. So we try to perform some kind of aggregation. What that aggregation could be. So what we do is we look into all of the neighbor states. So we talked about these yellow and the greens, and then we aggregate them, and then we take a current state of the node, which is this the black one that you see, and then we combine everything using some kind of a nonlinear activation function, and it will spit out a next state. Let's say that is a red. Now, how this works out, it depends, right? And there are if you look into these two activities, so you have an aggregation logic, which is that taking all of the neighbors. So what you see is for every neighbor of V, and then we do something, and then we just combine this into using some kind of aggregation function. And just to probably keep in mind, it has to be what you call as a permutation invariant operation. So what does it mean? So let's say that the order should not matter. So for example, when you are doing a sum operation, you can do 1 plus 2 or 2 plus 1. Or if you're doing a max operation, it is a permutation invariant. It doesn't depend on the order in which the inputs are arriving, because you don't know whether this is it should come first or this item should come first, right? So hence the permutation invariant operation is the key here. And once we had aggregated this information, we would like to combine it with the previous state. So what you see in a k minus 1 state, and then we apply some kind of an operation. Now, these operations is defined, depends, right? So for example, different papers and different implementation might use different functions. So for example, in the Craft Sage implementation, they're using a max as the operation for an aggregation. And then let's say a GCN paper, which was by Kiff and Welling, they used mean or essentially average as an operation, and they used ReLU as and obviously it's a weighted average, and they used ReLU as a nonlinear activation function. So again, the choice of these aggregate and combines, it varies with different implementations. But all in all, suppose that after doing all of these operations, and we come up with an updated embedding. So all of these became red, right? So which is a next version of representation. And we keep on doing it. And obviously you need some kind of a loss function that you'd like to optimize. And in most of the recommendation engine world, max margin loss is one of the very popular one, especially when you combine that with negative sampling. So what exactly it is? So what we are trying to do here is that we are looking into positive pair, where you see there is a strong connection because they have been bought or probably they have been clicked. And then you combine that with a negative sample where you don't have any interaction. And what you want to maximize is the difference between the positive and a negative. And you also apply in margin, and that's where this entire margin loss comes in, which essentially signifies how much this positive similarity should be compared to negative. So higher the margin, and you want both the positive and negative to be apart, right? So this is what a loss function that being used. But all in all, once you train the model, all of the neural networks are trained, and you have your final embedding or final representation with you. So once you have this, the job of a prediction or actually making a recommendation is pretty straightforward. So suppose that if you want to identify whether this customer will go for the item number 2 or not, you simply take these two pairs. And since we have a representation for both, an embedding for both, we can simply compute some kind of a similarity score, a cosine similarity or any other kind of a similarity score that you can apply, and it will spit out a score. And you can do that for all of the user item pair combinations. So let's say that for this user number 2, we want to compute this score for all the 4 items. And then maybe we simply rank the items based on score, and it will give you a ranked order of your recommendation. So this is how the entire recommendation engine works in a GNN setup. Now we'll go through some of the very popular implementations. So this probably yeah. One of the popular implementation is by UberEats. So in fact, there is a really nice blog. You should probably watch out, look at it if you have time. So for them, what they're trying to do is they're trying to recommend dishes. In fact, they're also trying to recommend restaurants, right? So how this works out. So what they essentially ended up doing was they created very similar bipartite graph. So you have different users, and here you have different dishes or food items. And they also have some additional information, which is, let's say that this user has, let's say, ordered pizza fast 5 times. So you're also introducing, which is the weights are being used here, which is nothing but a frequency of orders. So as you can see, this is a really nice representation of in a bipartite graph format. And in the UberEats implementation, they also used word2vec, we actually talked about earlier, on the dish title itself. So for example, let's say if you are actually interested in pizza, you might be interested in different kinds of a pizza than anything else, right? And that could be served from different restaurants though. So hence they actually opted for using this kind of a tool like word2vec representation as initial representation for item embedding. And then obviously it goes through the entire learning process. So in the paper, obviously they used a very similar aggregation logic. In this case, they also applied weights because they have the weights, which is nothing but a frequency of order. So how many times a pizza was ordered. So this was the aggregation logic. And the margin loss, again, they also used max margin loss, very similar to what we already discussed. But they also, probably in their paper, they also have introduced a slight variation of this loss, which is beyond just a standard positive and negative. They also had a low rank positive. So for example, if there are items which are being, let's say, ordered only once, suppose that you ordered some dish from a restaurant only once and you never ordered it again. So in a way, you are giving an indication that I may not have liked it, right? I might have tried it out once, but I may not have liked it. So hence, they wanted to introduce another kind of a penalty for these low rank positives as well. So this is a slight variation in the loss function. But all in all of this graph-based representation and the graph neural networks help them to probably improve their existing model performance almost like significantly. In the paper, obviously 12%, and as they mentioned that they kept on improving this. There are other popular implementation that you should be aware of. One is what I call as PinSage, which is being used by Pinterest. So Pinterest, what it does is that you have different pins, and what they want is that, suppose that if you have opted for 2 different type of pins, and you want to probably find out all the similar pins that should appear in that board. So in a way, again, it's a bipartite graph where you have the user boards on the left hand side, and then you have different items which are being essentially called as pins. Now, for Pinterest case, we are talking about a massive graph, right? Almost 3 billion pins and boards. So essentially 3 billion nodes we are referring to, and with almost 16 billion interactions. And in this case, since they also have these pins, could be text, it could be link, it could also be an image, they combined all of this information to provide that initial representation. So they used VG model to come up with image representation concatenated with a word2vec representation for the text information. And since this was a massive network, there are certain challenges, right, associated with how do you even compute these encoding, right, during the training process. So what they did was they applied what I call as a sample neighborhood technique. which is instead of looking into all of the entire network at entire graph at once, they identified use random walk and others to identify what is my sample neighborhood, and then use those as a batching so that they can run on GPUs. So subsample neighborhood technique, right? I'm not going into detail here. You should definitely read out the paper, a very interesting paper. What are the things, novelty they introduced in it? So we talked about some of the very popular implementations. So I'm going to just probably talk about some few more variations, very popular in the recommendation system world, especially if you're dealing with graphs. And for example, we can also add some kind of a more complex heterogeneous graph. So let's take the same example what we had earlier. So we had different users, we had different items, and suppose that we add one more set of nodes, which is interest and hobby of different users. And suppose that this user number 2, has an interest in food. So you may also want to use this information somehow. So for example, if this user has an interest in food, and probably she had opted for maybe an oven, and another user who also has maybe a food inclination towards food, may actually end up buying an oven, right? So as you can see that we can introduce more and more information, and all of this information can be used during the training process to update the embedding. So more information, better recommendation. There are a few more variations. So for example, social recommendation, where you also want to take into account a social network of individuals, because we understand that what we buy and what we do, it has a huge impact by probably people around us, by friends and colleagues. So this paper, GNN for Social Recommendation, essentially leverages that aspect and brings in the social network aspect to update these embeddings during the training process. There are a few more variations. So for example, there is what called as a sequence recommendation. Suppose that this user is setting up, I don't know, maybe a gaming rig. So probably this person got a machine, a box, maybe a big monitor, maybe probably a fancy mouse, keyboard, and then maybe also got some GPUs and added to it. And then our job is to predict what is the next item that we should recommend that can come in this particular sequence. And we can use this by obviously by other users, right? What they have done. So for example, the other user ended up probably buying maybe a setup a table, as well as maybe a good high class headphones. Maybe you want to probably recommend that. So there is a slight variation into the nature of recommendation here. Here we are talking about, we are also introducing what I call as a temporal aspect, and we would like to bring in what is the next thing that we should be recommending. It can be used for predicting next best action, which is very popular into a web world, right? For example, if you are going on probably a website and you want to predict what is the next action this user is going to do, and we can use that information to proactively push content based on where this user is in their journey. So again, there are some implementation. I'm just probably referencing it here. You can go ahead and look into the details. But all in all, this approach, for example, dynamic GNN for sequential recommendation, how they have approached is they have created a graph that includes sequence as well, right? And then use that to train the model. There are some more variation. Another popular one, what I call as a knowledge graph aware recommendations. So suppose that we had this bipartite graph on the left, and suppose that we have also created a knowledge graph, maybe on all of the different products which are there in the system. Suppose that this is oven which is being manufactured by Samsung, which is maybe an headquarter in South Korea, and we have this another leather bag as well, which is being manufactured by another company, which also happens to be headquartered in South Korea. Maybe this user really likes more South Korean products, and hence we should use all of this external information to generate much richer recommendation. That's an idea. So what here in this system is we're introducing another set of knowledge or another set of inputs through this knowledge graph. And that can also be baked into your recommendation. So again, some really interesting papers are coming into in this space. So watch out for it. So all in all, we have seen graph neural networks, some basic versions, some of the variations. For example, we saw social recommendations, we saw sequence recommendation, we saw knowledge-aware recommendation, we saw very standard graph neural networks. So if we taking a step back, these graph neural networks are really awesome, right, for recommendation systems. So if we have these, we started with these key challenges, if you recall, right? We said how to represent users, how do you build hybrid systems, how do you model dynamic behaviors, how to use implicit feedback. And graphs probably are a natural fit because they can exploit, graph neural networks can exploit both the content feature. We already saw an example around how you can use user metadata attribute and item metadata attribute, along with the network structure, which is essentially the user item interactions and different kind of an interactions in a very natural setup, right? Very easy to model some of these factors. Graphs are also dynamic, and we talked about that inductive nature of a graph. So that means is even if you more and more new nodes are getting introduced, you can still use them without doing an extensive model training, right, on a more regular basis. So you can still use your existing embeddings to create and calculate embedding for new nodes. And last but not least, the graphs can model much richer node features. So it can look into the content, let's say a text information, and then just apply some kind of embedding for that. It can use image as an input. It can also have additional information, and we saw how the social networks or knowledge graph can be used as additional information to enrich the recommendations. So this was a quick overview around graph and graph neural network, especially in the recommendation system setup. I just close it on a couple of things. One is what does it even take to build such and run such kind of recommendation engine in real world? As you might have guessed, it's not just a model itself that is needed. Probably if you see the entire recommendation engine setup, and here is a reference architecture, it will require a lot of many components. So on high level, so let's say that you have a data ingestion and processing pipeline, because you may have different kind of a data signals, real-time, batch, product metadata attributes, and you're enriching all of these product metadata, and all of it. And then we take all of this data and feed it into some kind of a model and testing framework. So where you are training these models and doing maybe offline evaluation, running some kind of an A/B test, or maybe some kind of a multi-arm bandit algorithm to adjust which kind of algorithm works, which kind of algorithms do not work. Deploy these models. You can have ensemble of the model instead of only one. And then you deploy and you run these perform an inference, which is running a recommendation engine, because it has to be fast, right? So you need a very fast machine learning server. You may have to just have an API because you want to decouple your recommendation engine with the rest of the systems. You may also have to cache your recommendation. Suppose that it is taking too long of a time to compute these recommendations. Sometimes you might want to compute this offline as well. So there are a lot of systems which does that. If you're doing online, you have to ensure that you have a fallback mechanism. And then you might have to retrain some of these models based on your need. All right. So all in all, as you can see that your models, which is maybe here, right, it's just one part of a puzzle. And there are so many other components that goes in to build a more robust real world recommendation systems. So hopefully you got convinced around why recommendation engine you should be reading about it, why graph you should be reading about it, and how graph neural networks and graph representation learning can be useful into this new era of new age recommendation engine. So if I got you excited, where to go from here? And so you can apply these and build some of these models. There are some of the frameworks which are already out there. Some of my favorite ones are PyG and BYG 2.0 is there, which is more PyTorch based implementation, and it has a lot of modules for building very sophisticated graph neural networks. Deep Graph library or DGL is also very popular. In fact, the benefit here is, sorry for the typo, is a PyTorch. The benefit here is that DGL supports different kind of a backend. You can use PyTorch, you can use TensorFlow, or you can use MXNet. And there are TensorFlow Keras specific as well, right? A Spectral, and there are a few more like GraphNet and others. So there are a lot of frameworks out there, so that you don't have to probably build everything from scratch and ground up. You can leverage some of these frameworks and libraries to build these kind of graph neural networks very easily. If you want to learn more about it, here is probably my favorite book is around graph representation learning, as well as this network science, really interesting, focusing on overall in general what the graph and what are the insights you can extract. There are a bunch of material out there, courses and whatnot on YouTube and others. So yeah, so thank you. I can take any question if we have.
There doesn't seem to be a question in the chat right now.
Okay.
Um, if anybody wishes to contact you, how can they do so?
Yeah.
Through Twitter?
So they can just reach out to me on LinkedIn or maybe on Twitter. I think that will be the most ideal way of reaching out. LinkedIn will be much easier because I look at it more than Twitter, but that's also fine.
Yes, that's great. Actually, a lot of people had interest in this talk, but probably because of the timing, they weren't able to attend it. So I'm sure
Yeah,
they would look at it further and contact you with their questions.
sure,
Um,
absolutely.
yes, it was great to have you here, and we can end this talk right now. Thank you so much for coming to MLRW, and we were really pleased to have you.
Thank you. Thanks a lot, team. Thank you. I appreciate it.